Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very happy to have Irit Dinur, who will tell us about probabilistically checkable proofs. As many of you probably know, Irit has been doing a lot of beautiful work in this area. And the good news is she's going to be with us for a whole year. So if you haven't had a chance to interact with her yet, then now's the time. You'll get a chance to know what her work is and talk to her later in the year, hopefully.
Thanks. Yeah. Okay. Right. Good. So it's going to be a general talk, right? So please stop me as much as you can because it's not too long. So we start with this story that I heard as a student, and now I'm telling it to the next generation of students, and really, you know, I've been searching for a better story, but
Jeff, can you raise the volume?
Okay, so you know, the story goes: if you get a proof from someone, and you want to know if this proof is correct, you have to read the entire proof. Really, you know that bugs hide very deeply and very well inside proofs, so that it's very hard for us to find them unless we read carefully every single thing in the proof. And sometimes this is tiring and, you know, annoying. Luckily for us, we don't really need to bother reading the entire proof, right? Because we can actually ask for the proof to be written in another language. In this. Okay, should I start all over? Is it okay? I mean, you guys should be hearing me, right? You can't hear me?
I can hear you, but I can't hear you.
Okay, so anyway, luckily we can ask for the proof to be supplied in this other format. So it's just a different language, so to speak, called the PCP format. And in this language, you don't really need to read the entire proof. All you need to do is randomly select 3 bits according to some very specific distribution and read only them. And based on their value, you can decide if the proof is good or bad. And you'll have some probability of error, so it'll be, say, 1/2. But that's not to worry because you can repeat this k times. And after you've done this k times, your probability of error is going to be really, really small. It's going to be 2 to the minus k, which honestly, for me, if I read a regular proof, my probability of error is much larger than 2 to the minus k. So, you know, it's okay. It's not really a big deal that there is some probability that the proof was false, but I didn't detect it, because k can be large. Okay, so this is kind of fantastic, right? I get 2 things. First, I get this very robust behavior that even if there was a bug, I know that I would find it with very high probability, and I don't need to work too hard. So that's really very nice. And the PCP theorem says that, yes, there is such a format for writing proofs. So that's the main topic I want to talk about today. And of course, at this point, we are all thinking, well, why aren't we doing this? Why aren't we writing our proofs in PCP format? And the answer is because this doesn't really apply for our proofs. It only applies to what we call mathematical proofs, right? So orthogonal to what we're doing.
How long do the theorems get, though?
The theorems stay the same. The proofs get a bit longer in this format, but thanks to some people in this audience, not too much longer. So it's not such a big worry.
So what we are doing is not mathematical proofs?
So so getting back to that, we are only doing literature. You know, there is this Gödel incompleteness. You never expect a formal proof system to capture all of mathematics, and we're working outside this formal framework. So what is a mathematical proof, or more precisely, what does the PCP theorem apply to? Okay, what kind of proofs are we talking about that the PCP theorem applies for them? These are proofs that can be verified by a rigorous procedure, by an algorithm. Okay, our proofs, there is no algorithm that reads them yet, but these are anything that really there is an algorithm that reads the string that's supposed to be the proof and says yes or no. So actually, the algorithm is what specifies the format of the proof. Okay, so let's start with like an example. When you think of a rigorous proof system, usually what I think about is this like Euclid's elements, where you have a bunch of axioms, and there is some rule to say if you take a couple of statements that we already know are true, you can derive a third statement by applying some derivation rule. And Eli actually talked about that a lot in his colloquium talk. So this is one example of a proof system. It's a sequential proof system where every time you derive a new statement and you continue this way. And of course, you can imagine that there is an algorithm that checks. If one is given such a sequence, you can check that this is a valid proof, or maybe you see that at some point some derivation was made that is false. Okay, so that you can understand that it's automatic. But really, there is no need to confine yourself to this. There's no need to just think of these specific proof systems. Anything that can be verified by an algorithm is good enough. So it's a much wider set of proof systems. And really, any computational problem or any algorithm gives rise to a proof system. And the way you think about it is you say, well, the problem is like a statement saying this problem has a solution. So this can be viewed as a theorem. And then the proof for that theorem is just the solution. Okay, so for example, if you think of some polynomial equation, this polynomial equation can be interpreted as a theorem that says there is an assignment to the variables, or there is a solution to this equation. There is an assignment that causes this equation to be true. And then what would be a proof? A proof would be an assignment to the variables. You can plug it in and compute and see whether or not you get equality.
This problem is undecided.
Yeah, but then how would you verify it in
not be a solution?
Sorry?
Then the proof would not be a solution.
Yeah, but I want to avoid this kind of stuff, right? Because I'm saying, anything that you have a rigorous...
algorithm that checks if something is a proof, even of that statement. You can actually, people have done this, you can automate, write down formally the proof of Gödel's incompleteness theorem. And some people have done it.
Sure, I'm aware, but I don't think that then the proof is a solution to the problem.
The solution is the proof. There exists a string such that...
Also, the problem is, does there exist a proof?
Yeah,
Exactly.
the problem is, does there exist a proof?
No, but this is a syntactic equivalence. You can say the...
Okay, I got.
But you're dealing with search problems, right? So that it really is like a solution.
This can be phrased as a search problem where you're saying, find me a solution. In other words, find me a proof. Yeah, and the equivalent decision problem is there exists one. There exists a solution, there exists a proof.
Right.
Yeah. Right. Okay. Okay, yeah. Yeah.
Can you give an example of the kind of statements that are valid theorems? Like that this does apply to, as opposed to what it doesn't apply to?
Yeah, thank you. Yeah, so it's the next slide, right? So I'll do the next slide. Right, so just to say, I guess this is just a comment that in the way I described it, an example was like you have an equation, and then the proof is a solution to this equation. And then you can ask yourself, well, what's the difference between the equation and the solution? It looks like it's the same kind of thing. And the answer is, well, from computational complexity point of view, there are different things, right? Because if you get an equation, maybe it's very hard for you to find a solution. But if you get a solution, it's usually much easier to verify it. So in complexity, we have a nice way of differentiating between theorems and proofs just by measuring how long it takes to verify the correctness. Okay, I can see that maybe it's still not clear because it's kind of in the air and there's no context. So my next couple of slides are just going to be examples, and then maybe we'll have a better... so here's an example. Okay. So instead of formally defining what a computational problem is and what a proof system is, which is the same thing, want to give a couple of examples, and then we'll say formally what it is. Okay, so here is the first example, linear equations. It's a very basic example. So you have a bunch of equations over some finite field. Think of 0, 1. So just GF2. All the equations are modulo 2. You have a list of equations like this. And this is your input. So it's like, this is the problem. Or in other words, this is the theorem. You can interpret this as a theorem saying, this set of equations has a solution. Or you can think of it as a problem, you know, find me an assignment to the variables that satisfies all of these equations. This is two equivalent ways of viewing this. And then, right, and so there is this algorithmic goal, right? Decide if there is a solution, right? And in this case, this is actually an easy algorithmic problem. We know how to do Gaussian elimination, and we know how to find in an efficient manner a solution for this problem. By the way, if it's overdetermined, then it's not easy anymore. So what does overdetermined mean? Suppose I have some m equations, and there is no way to solve all of them. Okay, there is some contradiction. When you do the linear algebra, you see that the solution space is empty. So still, you know, maybe this is the result of some measurements, and you want to find a solution that satisfies the largest number of equations. Say, satisfy over 90% of the equations. This seems like a very reasonable task. It should be, you know, it should be something that we are able to do. And the fact is, we are unable to do it. We don't know of any algorithm that does that. We don't know of any algorithm that, having the guarantee that even if you know that there is some solution satisfying 90% of the equations, you don't know how to find it. In fact, we believe that it's hard. And it is NP hard. Okay, so we believe that it's not possible. It is NP hard. It's not that we believe that it's NP hard. It is NP hard. We believe that NP is hard. Thank you. Right.
In this case, 90% is a part of the input.
Sorry?
90% is a part of the input, right? You give the problem and you give
the 90%. Yeah, in fact, any number above a half is already hard. But yeah. What do I want to say here? Okay, so when I say hard and easy, of course, I need to mention that I'm talking about as a function of the length of the input. So that would be the number of bits it takes to describe this entire system of equations, right? So we have polynomial good, exponential bad. Okay, here's a second example. Okay, it's only two examples. This is going to be 3 coloring. So the input in this case is a graph, so a bunch of vertices and edges between them. And the goal is to decide if there is a way to 3-color the vertices of the graph, meaning to map each vertex to a number 1, 2, or 3, such that every edge sees 2 different colors. Okay, so that's the goal. Find a way to color the vertices so that every edge sees 2 different colors. And again, you can view this as a theorem saying, you know, this graph is 3-colorable. Or you can view it as a problem saying, you know, find me a coloring for this graph. Or is there a coloring for this graph?
I thought you were going to ask us, is this graph plane?
Is it? Yeah, it is.
And 3-colorable.
And 3-colorable. Yeah, okay. Okay, so that's my second example. And in this case, see, it is 3-colorable, right? Like Buzz saw. Yeah, it is. Okay. However, unlike this graph, in general, it's hard to solve this problem. We don't know of a way to find the 3-coloring if we see a graph. Again, it's NP hard. But what is true is that it's easy to check a proof. Okay, so if you give me a coloring, it's very easy for me to verify that this is a valid proof. Okay, so I just go edge by edge and check that this coloring is okay. Okay, so having seen 2 examples, let's say what a computational problem is. We just identify a computational problem with the set of all correct or solvable instances. So for example, here it's the set of all 3-colorable graphs. Okay, in the case of linear equations, it's the set of all equations that have a solution. Okay, so you can think of it as being the set of all yes inputs, or you can think of it as the set of all true theorems. Okay, so any string is a theorem. Some of them are false. You know, some graphs are not 3-colorable, But the three colorable ones are the truth theorems in this proof system. Okay, so let's do this P and NP and all that. Okay, so we have the class P. It's the class of all computational problems for which an algorithm can decide if the problem is solvable or not. And then there is NP, where it's a computational problem where maybe you can't figure out for yourself, but if you see a solution, you can check that it's correct. So for example, three coloring is in NP. And in some sense, NP, if you think about mathematical proof systems, this is the broadest class. Because what is NP? It just says, whenever I have some rigorous procedure for checking a proof, I'm already calling this a proof system. So any proof system you can think of where there is a rigorous way of checking the proof, and this way is also efficient, this is a problem in NP. Oops. Yeah. Oops. Okay, so that's NP, and then there is the million-dollar question of whether P is different from NP. And an interesting phenomenon in NP is that we know what the hardest problem is. Okay, although we don't know if NP is equal to P or not, we do know that three coloring is the hardest problem in NP. Okay, so what do we mean by that? If you solve three coloring, you solve everything in NP. This is what it means to be NP hard. And sorry?
A hardest problem.
Yeah, it's a hardest problem. It's not the only one. That's true. And how do we even make such a statement? This statement is true because we have the following notion of reduction. So a problem is said to be NP hard if you can always use it to express any other problem. So if you have any other problem in NP, then say some A problem in NP, then any input for A can be efficiently mapped into some other input R of X that is in your problem, say three coloring. Okay, so there is an efficient way to map inputs in some A to inputs in three coloring. And you know that these will be solvable if and only if those will be solvable. Okay, so that's this notion of reductions. And this means that three coloring or any other NP hard problems that we talk about is very expressive. It expresses the full power of NP. It's like a language, just like you expect that you can say anything you want to say, you can say it in English. You can also say it in some other languages. So three coloring is also a language. It's a language that is, although it looks to us very strange to express all of our theorems as statements of the form, this graph is three colorable or that graph is three colorable, but it's just expressive enough. It's strong enough to express anything in NP. So in other words, any other problem in NP can be translated into three coloring of graphs. Okay, so it's even more than that. If you want to prove to me, say, that some system of equations is satisfiable, all you need to do is take the system of equations, map it into some graph, and tell me, this graph is three colorable. Okay, so there's not only one way to prove to me that a system of equations is satisfiable. You can also use a different kind of proof system that says, you want to know whether this system of equations is satisfiable? Here is a graph, and the proof will be that this graph is satisfiable. Okay? So this raises some interesting possibilities. The fact that one problem can be mapped into different NP hard problems, and for each one of them there is maybe a different verifier with different properties, suggests that maybe you can use these different features of these other verifiers to gain something. Okay? And indeed, in some sense, this is what we do in this PCP world. Okay, so now this finishes the introduction, and now I want to talk about what the PCP theorem is, and then show a proof of it, and so on. Okay, so the PCP theorem is now 20 years old. I guess we should have had some celebration, right? Is it 92 really? Ah. Okay. Okay, so we should start preparing the celebration. Okay. So it was proven by Madhu et al. And the background for this theorem was, it actually came from people thinking about complexity in cryptography.
So wait a second. There are two competing groups who proved
No, you're not competing.
It's two papers. One proved with some parameters that were not optimal, and then the second group completed the work. So it's attributed to both papers. Yeah. But there is some intersection in these groups. Yeah. Yeah, it'd be interesting to say these are brothers, and and they didn't speak. But it's not true. I'm just saying it. Okay. So okay. Anyway, what I wanted to say is that kind of the background was that people thought about different kinds of ways of proving things between computational entities. In cryptography, you have this thing. You have interactive proofs. And in cryptography, it's very natural to think about randomness. In fact, there is nothing in cryptography if you don't have randomness. And so it was natural to say, look, we have these NP verifiers. Let's add randomness to them and see what happens. And so this is what happened. OK, so let's now see the formal definition of what an NP verifier is. And then we will add these gray things to make it into a PCP verifier. OK, so when do we say that a problem is in NP? So I have some problem A. And I think of it like three coloring. OK, so keep in mind three coloring. What does it mean for A to be in NP? It means that there is some efficient algorithm, which we call a verifier, that gets two inputs. It gets the input, what is supposed to be a theorem, say some graph. The statement is this graph is three colorable. And it also looks at a proof string, which is supposedly maybe a coloring of this graph, maybe some other proof string, I don't know. And then the verifier reads these two things and makes some computation and says yes or no. Okay? And the two conditions that must hold are that if the theorem is in A, it's a correct theorem, there must be a proof causing the verifier to accept. And if the theorem is not in A, it's a false theorem, then every single proof must cause the verifier to reject. That's our natural notion of a proof, right? If there is the graph is three colorable, there is a way to convince me, and if it's not three colorable, then nothing will convince me. Okay, so the PCP verifier adds some more power to the verifier, and this power is in the form of randomness. So now the verifier, in addition to the input string, it also has.
The verifier that reject. It only has to accept one of the possible proofs.
Interesting. So what defines a valid proof? So Christian says there could be a valid proof that the verifier rejects, but the validity of a proof is whatever causes the verifier to accept. Okay, that's the way we define a proof system. It's just the verifier is what defines.
Right, so I could prove to you that the graph is recolorable. Jennifer has a different proof, and your proving system doesn't accept my proof.
That's right.
That's allowed, right?
Yeah, just like I prove to you, but I speak in some language you don't know. So, I mean, too bad.
Quote by that Shimon Evan once defined in a class, the proof is whatever convinces me. So
I see. I saw this in some other thing, but I never knew it was. Okay. Okay. So in the PCP verifier, we now, in addition to reading the input and the proof, the verifier also reads some additional string, which we call the random string. But for now, it's not random. It's just a string of bits. And in return for the fact that we give this verifier randomness, we expect something. And what we expect is that the verifier doesn't read the entire proof. It will only read a very small window in the proof, just a constant number of bits. OK, so this is some restriction that we impose on the verifier. And the point will be that even under this restriction, we still have such verifiers. OK, so we added a random string, and in return, we restricted the verifier to read only a small number of bits. And again, the verifier then accepts or rejects. And what happened to the completeness and soundness condition of before? So the quantifiers in front of the theorems and in front of the proofs should remain the same. For any proof system, you don't want there to be some randomness saying, for most theorems I can prove them. this is not a proof system. Or for most proofs, I can accept them. Again, this is not a proof system. A proof system needs to be, for every proof, for every theorem that's correct, there will be a proof. And for every theorem that's incorrect, every proof will not convince me. Okay, so this still is the same. See, for every theorem that is correct, for any, say, three-colorable graph, there's going to be some proof causing the verifier to accept. And then there is this green thing saying something about probability. So the probability is over what the verifier is doing. So with high probability, the verifier will say yes when it's supposed to say yes. Okay, so here it's even with probability 1, but even if I had here probability 2/3, it would be okay. And for any theorem that's incorrect, for a graph, say, that's not three-colorable, and for every single proof, there's no randomness over these things, the probability that the verifier accepts, and now here's where we have a probability over the random string, right? So for every single random string, the verifier is doing a different action. And for many of these actions, the verifier is going to reject, for more than half of them, say. Okay, so sometimes it will still accept. That's too bad. It should have rejected. But at least half the time, we know that it will reject. Okay? So at this point, you can say that's not very convincing, because to get correctness of probability half, I don't need a verifier, right? I can just flip a coin, and I already know if the proof is correct with probability 1/2.
Right, efficient verifier. Do you, in addition, want that the verifier only takes polynomial times?
Definitely, yeah.
Okay.
Yeah, this must be. Otherwise, it's not a proof. I mean, I can always say go over all possible solutions myself. I don't need a proof for being inefficient. Okay, so I just want to point out that this 1/2 shouldn't really concern us, because we can repeat this. Okay, so if you just repeat the verifier on independent random strings k times, the probability of missing or not detecting a problem when there is one goes down to 2 to the minus k. Okay, so that's already, very good, right? As we said before, this is almost 0 in human standards, right? So so again.
So if you repeat it, I'm curious, where does it say that it's independent in the definition? That, like, if you choose some random bits, that'll be...
The definition says that for every false theorem and for every proof for it, the probability over the random strings is less than 1/2. So if I choose 2 random strings independently, the probability that both of them will get into the accept range. So, what does this mean? It means that for half the random strings, I reject, and then for half of them, I might accept. But the probability that I get twice into that set is 1/4.
It's over the set of all random,
yeah. Yeah. So in other words, this is really as strong as you would like it. It means that really the probability can go down to 0, and it goes down to 0 as fast as you can expect.
The number of repetitions, it doesn't need to be bounded by a constant.
It doesn't need to be, but every time you repeat, you read some additional bits from the proof. So if you want to say, I only read a constant number of bits from the proof, you better repeat only a constant number.
But the number of repetitions
can be anything.
Because if you take a coloring where you violate just one edge, you probably need to repeat this something like n log n times before you actually discover that.
Oh, that's a good point, which I will get to later on. That's one way of doing a proof of 3 coloring, but actually that would make me read the entire graph, pretty much, right? So why do I even need to do this probabilistic thing?
It's here because it's constant number of bits per trial, but the number of trials is large, and you're right, you might just as well read the entire proof.
Yeah, so that's actually not a PCP for 3 coloring.
The probability of accepting is much bigger than
here.
No, but there,
The 2-second bullets, the second
Oh,
one
this.
there.
Okay. Oh, I see. Okay. So the point is, you need these two to hold simultaneously. Okay. So it needs to be a constant number of bits and probability less than 1/2. In what David is suggesting, you can get a constant number of bits, but the probability of accepting can be as high as 1 minus 1 over the number of edges, which is bad. But okay, actually, we'll get to that soon or less soon. I don't know. Okay, so just to say, this is why does this appear striking? It's because we are used to thinking of proofs as something very, very sensitive. There should be one bug hiding somewhere that falsifies the entire thing, right? And somehow this says, there is another kind of format where if there is a bug, the bug is evident half the time. So, oops, yeah, somehow. Half the time, whatever the verifier is doing, it sees some bug. So it's kind of non-intuitive. Okay.
Does the verifier expect the randomness come from some specific distribution? Or?
Uniform. Yeah. Just think of it as the easiest setting that you can think. Yeah. Okay, good. So now we get to this three coloring. Okay, so what is the natural, whatever, the first thing you would think of a verifier for three coloring? You get a graph, and you want to check that it is three colorable. So the proof will say, the color of vertex 1 is 1. The color of vertex 2 is 2. The color of vertex 3 is 1, and so on. And the verifier will just go edge by edge and check that these two endpoints have different colors. Those two endpoints have different colors, and so on. Okay. Now, what would be a PCP verifier for this problem? I said the PCP theorem says that any NP language, in particular three coloring, has a PCP verifier. So there is some proof format that you can really read just a constant number of bits and be convinced with very high probability. Okay, so what would be a PCP verifier? Okay, so the first attempt that one would try is, do the same thing, but instead of going, edge by edge, very tiring, just select a random edge. Select a random edge and check if those two endpoints have different colors. If yes, you say yes. If no, you say no. Okay, so what happens? Okay, before I say that it fails, if the graph was three colorable, then I will always see a good, and you gave me a good three coloring, I will always say yes. So the first part carries through. But the second part fails. The second part says that if the graph is not three colorable, then no matter what proof I'm given, I should reject with probability 1/2. And the fact is, a graph might be non-three colorable, but it can be very close to a three colorable graph. Maybe there is a coloring for this graph that satisfies all edges except for one. Okay, such graphs, of course, exist. And if I happen to land on such a graph, then this procedure will accept with probability, like we said, 1 minus 1 over the number of edges. Okay, so very, very close to 1. Okay, and even if I repeat this 100 times, it will still be very close to 1. In fact, to drive it down to a half, I need to repeat it on the order of magnitude of the number of edges, right? Which means I've read many bits. I haven't read a constant number of bits. Okay, so that's why this is a bad, this is not a PCP verifier. Something else I wanted to say. Yeah, I don't know. Okay. So instead, you need to find some other way to encode this, the standard or the natural proof of three coloring into some other format of a proof so that you can do this probabilistic verification. Yeah, just the thing I wanted to say was just that you might say, well, your graph was very strange. It had this behavior that it had almost a coloring. It just violated one edge. So we should probably discard such graphs. This is not the definition of NP. In NP, we're looking at worst case behavior. So it's not that for most graphs or something like that, these things happen. A proof system needs to be able to prove for every single theorem, for every single graph. If it's three colorable, you should say you should have a proof. And if it's not three colorable, you should not have a proof. So this is why this fails. However, still we're going to focus on graphs on which this doesn't fail. Okay, so let's call them for now a robust graph. So a graph, we will call it robust if every almost coloring, what is an almost coloring? It's a coloring that satisfies almost all of the edges. Okay, so you're still using three colors to color the vertices. And now you're just asking yourself, how many of the edges have I satisfied? So in the bad case that we discussed before, you had a graph that has an almost coloring. There's a coloring that satisfies everything except for one edge. but it doesn't have a perfect coloring. So we're going to now rule these things out, and we're saying, look, a graph is called robust, and that's a good thing for us. If whenever it does have an almost coloring, then this almost coloring is somehow correctable into a perfect coloring. Okay, think of it like an error correcting code. You have some string that's almost good, then you can just move it into something that's perfectly a code word or something. Okay, so these graphs, let's look at them. And now, okay, let's also denote this. The value of G will be exactly this fraction of edges that are satisfied by a 3 coloring. So you go over all possible 3 colorings, and you see what's the one that gives me the best fraction, the largest fraction of satisfied edges. Okay, so for example, a 3-colorable graph would have value 1. So for a robust G, 2 things can happen. Either it's a 3-colorable graph, and then the value is 1. That's fine. Okay, there's the word has missing here. Or it doesn't have a perfect coloring. But then, because it's robust, we know that it doesn't even have an almost perfect coloring, right? Because by definition of robust, if it had an almost perfect coloring, then that coloring would be correctable. Or in other words, there would be some other perfect coloring hiding out somewhere. Okay, so for robust graphs, we know this dichotomy behavior where the value is either 1 or it's less than 99% or something. Okay, and of course, if we have a robust graph, then our problem from before wouldn't happen, right? Then this very simple verifier will really work well on it, because you're guaranteed that if the graph is not 3-colorable, there's a good epsilon fraction of the edges that show it, and then once you hit one of those edges, you're good. Okay? Okay, so the main point is that to construct a PCP verifier for any language, all you need to do is have this robustifier, right? Some algorithm that takes your input graph and outputs some other graph H, which is like the robusted version of G, and with the property that if H is 3-colorable, if and only if G is 3-colorable. Okay, so you take your G and you do something to it, and now it becomes robust. Okay, this is the main point. And then once you've done that, the PCP theorem follows. So obviously, right, if I have any arbitrary graph G, it's not robust or anything. First, I make it into a robust graph using this algorithm. So it's an efficient algorithm. I can do that. And then I just expect as a proof a coloring for the new robust version, right? So I get that proof, and I run the naive verifier, which basically selects a few random edges and checks only them. Okay, so I know that if my original graph was 3-colorable, the robust version is also. So there is a proof that would cause the verifier to always accept. And if it's not 3-colorable, then the robust version isn't either. And because it's robust, it doesn't even have almost colorings, right? So any coloring for it now has this epsilon fraction of bugs out there, and the naive verifier will hit them with good probability. So this means that I have a PCP verifier.
This is going to be a nitpick, but I don't really understand this point. If you choose a random edge, then in order to see if it's colored, if it's proper, you'd have to check both vertices.
Right.
But now that you're checking both vertices, it's no longer random. Right, it's not uniformly random.
It's not uniformly random. That's absolutely true.
So it doesn't have to be...
It has to not be uniformly...
Oh.
Actually, yeah. I mean, it's always going to be some special distribution that's not uniformly random.
Okay, so you can just choose part of it randomly, but...
Yeah, when we say random, we just mean like there is some distribution over which you choose your...
It's a distribution on joint set of queries. So
got it.
You query things, and there's a distribution on the joint thing.
Yeah.
Okay.
Yeah.
What you meant uniformly random before was the coins that the verifier tosses.
Right.
Yeah, maybe just ignore what I meant. What I meant before. I mean, it's really you have some proof, and there is some distribution over bits in the proof that you're reading. It's not independent. Certainly not.
No, I thought the original proof said that for every choice of things that you select, that the probability would be less than 1/2. But it's not every possible set of random bits. It's, it's...
Right, so what Boz was saying is that I choose a a random string uniformly random. But then from this string, I compute. For example, I use this string to select a number of between 1 and the number of edges. And then these edges tell me which 2 vertices they want to be read. And then I read these. So in the end, what I'm reading is not a uniform thing.
And at the end, you read actually more than 2 vertices, right? You then ask for 500 vertices.
Right.
For the color of 500 vertices.
Right. Because I repeat it 500 times or 250 times, depending. Yeah.
Hiding somewhere here, right? For
Yeah.
every G and epsilon, you can find corresponding H robust version, which would be epsilon.
Oh, yeah, it's a good point. It's not for any epsilon, but for small enough epsilon.
There is an epsilon.
Yeah.
So for coloring, there is some concrete number for which.
Yeah, for example, for large, if epsilon is close to 1, you can convince yourself that it's actually impossible to do this. Yeah, so there is some constant epsilon. Maybe it's 1/1,000,000. Of course, there is a whole industry trying to optimize these epsilons, right? And it's very important, of course. Okay, so just note that the robust. Oh.
You said that your posture was not taped because you're standing in a blind spot for the camera.
But my intonation. Okay. What?
Because it's important.
Okay, the quote. Yeah. Okay. All right. Last note that I wanted to make is that this algorithm that converts my graph G into this robust graph, this robusticizer thing, it takes G and it converts it to H. It doesn't know whether G is three-colorable or not, right? If this algorithm was able to figure out if G is three-colorable or not, then it could convert it into some constant size thing, right? Either it would be this K4 or it would be just a vertex, So in the first case, it's not three-colorable. In the second case, it is, and that's it. So, of course, but the point is that this is an efficient algorithm. And so we haven't solved three-colorability yet, so our algorithm doesn't figure out whether G is three-colorable or not, and yet it's able to do this robustification. Right, which brings us to this cartoon that I have, I borrowed from Bernard. It's kind of a metaphor for how the PCP theorem works, how it makes a proof robust. So think of this experiment. You have this piece of bread, and maybe it has some jam on it corresponding to a bug. Maybe it doesn't have any jam, right? And you don't know because it's a graph, and you have no idea if it's three-colorable or not, right? So even though you see the graph, and it's driving you crazy, there is no way for you to know if it's three-colorable or not. Okay, so it's like you're blindfolded, right? But there is still maybe jam on this bread. And then you do this experiment where you take your knife and you do this spreading motion over the bread, right? And then you end up with two possibilities. Either there was some jam to begin with, in which case it'll be spread all over the place. Or in the other case, there was no jam, in which case after you did this spreading, it's remained just like it was before. Okay, and now you can randomly taste this piece of bread in a random location, and you'll know whether or not it had jam to begin with, right? So
this implies that after you spread it, you can look at it and actually see if it has jam or not.
Taste it. You can taste it in a random location.
No, but
this is a problem in my metaphor. I was hoping.
Parents aren't a perfect metaphor either.
Thank you. There is a problem in this metaphor because I didn't. At least.
At least it's kosher.
I thought the metaphor should be that there's a bug, but you can't see it, and then you spread it.
The bug? Disgusting. And then you taste it? No, but the point is that with the proof in hand, you can actually taste it, right? Yeah, okay, it's not.
So the bread is a proof with a bug in it.
Yeah.
Oh, okay.
But whatever, it's yeah. There is a bug in the metaphor, but nevertheless, I worked so hard at this. Okay, so good. So now that we have the metaphor, we'll actually do the math that behind the gem spreading, right? So I want to now show or outline some kind of proof. Okay, so what is our goal? We want to map a graph G to a graph H such that if it was perfectly three-colorable, remember we had this value thing that said what's the maximal fraction of edges that are satisfied by a coloring? So if it was 1, it should remain 1. And if it was not 1, it should now be bounded away from 1. So I think the jam is more natural in this case. So think of it this way. If there was no jam, there is no jam. And if there was some jam, after this transformation, the jam value will be noticeable. Okay? And this jam value is just the deficiency, whatever, exactly those edges that are unhappy. Okay. So although it's the same word, this is not a metaphor. It's it's a mathematical definition here, right? Okay. Okay, so we have two different ways to prove this. The original proof maps the graph G into several steps into graphs H using all kinds of like algebraic encodings, using low degree functions and this kind of thing, and relying on the fact that low degree functions are robust in senses that are analogous to the sense we talked about G. So we'll get back to that at the end. Okay, right. And then there is the combinatorial proof, which does it in many, many steps, and each step is kind of just a small, spreading it a little bit further, and it uses the kind of the expansion property or some kind of expansion of the graph itself. Okay, and we'll talk about this second one.
So this one's like taking another piece of bread, and like slowly.
Which one? This one?
The second one, no. Take one piece of bread, it spreads a little bit more. I don't know. Okay, I like the metaphor. So.
The bread gets a little bit bigger.
Yeah, I like the metaphor too. Too bad it's not quite. We should fix it with some parrots and. Okay. Okay. So here is the general scheme. Is you do this jam spreading slowly, right? So you move from G1 to G2 to G3 and so on, and every time the jam value gets doubled. Okay, so you double it many times until it gets to be a constant. Okay, so this is the basic step. Remember, every time you do this doubling, if it was 0, it remains 0, but if it was bigger than 0, it gets doubled. Okay, so that's the basic step. And so how does that work? Okay, so there's really, yeah.
I mean, do we know why this suffices? Or why the basic step suffices?
We should know because we double it at every step. Oh, did I not say that don't worry about the sizes? What are you? Oh, yeah, okay, thanks. Yeah, you're right. Okay, so when we start out, the jam value is either 0, in which case it remains 0, according to this. And if it's non-zero, then it's at least 1 over the number of edges, so it's polynomial, right? So if you double it a logarithmic number of times, it becomes a constant, right?
But also the graphs can't be growing very fast.
Right. So this is actually very important. If the graph was going to be quadratic every time, then I can't afford to do more than a constant number of steps. Okay, so in fact, in this procedure, the graph will grow only linearly. So say the graph will be multiplied by 100, the size. Okay, and then again by 100. So after a logarithmic number of steps, you got the size became whatever it was originally times 100 to the log n, which is still fine. Okay, that's what.
It doesn't grow by a factor of 100. I mean.
Yeah, it can.
Because she only has to do it log n times.
In the basic step, it's a factor of 100.
Oh, right. Okay, got it.
Okay, yeah. Right. Okay, so let's do the basic step. So the reason that the graph only grows by a factor of 100, and this 100 is really like a trillion or something, is because you're doing something, everything you do is local. So for every, say, vertex, you're doing something local. For every set of few edges, you're doing something local. A set of few edges is not a very local thing. For every, I guess, edge or something we'll see in a minute, you're doing something local. So that's what.
Because your degrees are not necessarily bound, right?
Yeah. Okay. So, yeah. Okay, I'm actually in this talk. These subtleties are missing. But actually, so one thing you need to worry about is maybe your degrees aren't bounded. That's easily taken care of. You can take each vertex of high degree and replace it by a bunch of vertices of small degree, and while still maintaining whatever it is. For example, here we're maintaining 3 colorability. So there is a gadget that does that. It's not a problem. So we can assume that the graph is regular and has constant degree. Okay, so yeah, I know in some cases this is a big deal, but somehow here it's not. Yeah. Okay, so how do we do this basic step? We have two parts. The first part is like a gathering of information. Remember, our main goal is to convert a graph from a graph that maybe there is a bug somewhere to a graph where if there is a bug, it's everywhere. So somehow this information about the existence of a bug should flow throughout the graph, right? So, so we'll do this.
It's new to me that vertices know their colors.
They don't.
Don't they? When I see, okay, so let me read the sentence and then try to justify it. So the first step, each vertex gathers the color of its neighbors. So by that, what I mean is the following. A vertex doesn't know its color, but it has some, the proof will give it a color, right? So now you're saying, well, instead of giving it a color, I want the proof to give it not only a color of itself, but also the color of its neighbors. So you
But I thought that actually your gem spreading algorithm was supposed to be blind and not know yet whether it's colorable or not, and not interact with the prover and anything like that. It's supposed to do it blind. So
it certainly is blind.
See the colors. So what does it mean it doesn't?
Think of it, suppose instead of graphs and colors and so on, I had a system of equations over variables. And now I'm saying, look, I'm introducing a new variable whose value is supposed to encode the values of x1, x2, and x7. I'm allowed to do that. Even though you haven't told me the values of x1, x2, and x7, I'm just telling you, look, I have a new variable, and its value is supposed to encode the So think of each vertex as really a variable. In the coloring, it's assigned the value 1, 2, 3. And now I'm telling you, look, instead of assigning it just values 1, 2, 3, think of it as if it's receiving a value from a much larger domain. And this value is supposed to, it's not really, but it's supposed to encode the colors of all of its neighbors. Okay, so that's, when I said gather, it's only a metaphor to say the value that it expects should really encode the colors of its neighbors in the original graph. Okay, so that's the first step. So each vertex.
Each vertex in, I'm still not getting vertex. It's a vertex in the graph.
In the original graph.
A vertex in the original graph, and then for every set of colors in the original graph, any possible setup for the neighbors, something happens. I'm not quite sure as to what.
Okay, let me say it again.
Right? So you used to have that each vertex knew I have a variable which says which color I'm supposed to be, but it's a variable, it's not yet assigned.
Right, it's
and
a variable.
instead now of the vertex having one variable which says I would be red, green, or blue, it will have again one variable
D plus one variable.
Which sort of is 3 to the D plus 1, which would tell you the color of the neighbors and itself.
Okay, so you, instead of 3 coloring,
it's a 3 to the D coloring.
It's really complicated.
And it's,
right.
it's not coloring because the equation is not just inequality, but it's some.
Right. So now let's see what the. So really, right, we're moving from the world of 3 coloring to some world of constraints between variables of the vertices. So it's going to be the same set of vertices. Now each vertex will have some bigger variable encoding whatever something. It's supposed to encode really the colors of its neighbors. And now we're going to have a constraint between two vertices that have not only an edge, but actually a path of length something, say 3 here. Okay, maybe t for some constant t, but even think of 3. Okay, so for any path of length 3, we'll now have a constraint between v and u if they are connected at distance 3. Okay, and what is this constraint going to check? It's going to check that whatever both vertices say, in other words, whatever their variable contains, is consistent. So it could possibly be part of a global assignment that's correct. So for example, if I have here u and I have here v, okay? And suppose v, in its new big variable, it says the colors of all of its neighbors, and suppose it thinks that this guy should be yellow. Okay, and suppose u also has a bunch of colors and it thinks that this guy should be yellow. Right, so then there is a conflict because there is an edge here. And so these two big values can't be consistent with each other. So the constraint says, you know, this I reject. Okay, so it's a complicated constraint. It's not just saying this is different from that, but it's not too complicated. It's some, you know, the truth table of this thing is some constant size table. There's only a constant number of possible values, and for each pair of values, you can compute whether or not it's okay.
Is there a reason you should take 3, not 2? Because there's a test of consistency with length 2, right?
Yeah, there's no reason. Actually, you know, when you prove it, it's not length 3. It's length 100 or some constant. Okay, but it's easier to draw 3. There's no reason.
Definitely go smaller, but 3 is...
Oh, I don't know how much is enough. I wonder. I mean,
people who are doing these great estimates are figuring that out. Right?
It's an important problem.
It's an important problem.
No, I don't know that anyone is actually looking at this, but it's an important problem. Yeah, actually, why not? I mean, you know, these things are just asymptotic, right? So we never care about these things. Yeah. Okay, so after this step, which I called here the gather step, where somehow the information of each vertex is now, supposedly it has more information, it's supposed to gather more information. So you can already intuitively see that since each vertex carries more information, there is more chance of detecting some inconsistency. And in fact, you can prove that if the jam value of the original graph was something, the jam value of this is not a 3-coloring instance anymore. It's some constraint satisfaction instance. It's doubled, or maybe more. It got multiplied by something.
When you reduce that back to 3 coloring, you may actually reduce your...
You might lose a little bit. Yeah, you do. But you gain here more, and then compared to what you lose.
She's about to do her compensation.
Yeah, right. So now we do this disperse, where you bring it back to a 3-coloring instance. Right? I mean, I want to repeat this step again and again. So I know this step works on 3-coloring instances. I must keep staying in this world of 3-coloring, right? So I see too many confused faces. All right, so the disperse phase, and then I'll say it all over again. You take each vertex and you split it into a bunch of vertices, which are now, each new vertex is only going to have a variable that holds one of 3 colors. Okay, so you're back into this 3-coloring domain. And now the tests are somehow replaced by regular edges, meaning 3-coloring edges, edges that test inequality between two things.
Now you were trying ultimately to get to an H which was smaller than G.
No.
H is not supposed to be smaller in size, it's supposed to be more robust.
Yes.
Yeah.
Okay, because it's getting pretty big, it looks like.
It's getting
I mean, not
multiplied by some
right,
constant
it's just
factor.
a constant, it's just right. But
Yeah,
it's
actually,
kind of
it's a big constant.
Yeah, okay, good.
Have to agree, yeah. Okay. Okay, so let's kind of say it again. So we started out with a 3-coloring instance. Each vertex now, in the first substep, kind of took a bigger value. And we also put constraints between vertices that are a bit farther apart. So say distance 3 rather than distance 1. And these two things together allowed us to increase our this jam value. In another sense, if you knew that every assignment falsifies some fraction, then after this, every assignment falsifies a larger fraction. In the second step, you go back to the world of 3 coloring. So how do you do that? That's actually far from obvious here. And the answer is you do it by, here, there is a thing here, by recursion. Really, to convert each vertex back into a bunch of 3 coloring vertices in a way that is robust, it's non-trivial. And I'm not going to get into it here, but what you do is you look at just at this vertex and maybe one of these edges and another vertex as a small system, like a graph in itself, and you apply the PCP theorem just on that. And you can say, well, this is ridiculous. You're trying to prove the PCP theorem. But somehow, because this is a constant size object, it's easy to prove PCP theorems for those. It's not trivial, but it's possible, and so this we know, right? So somehow,
This is a different PCP theorem from the one that you are trying to prove.
right? It's a totally different. You're unhappy?
What's the induction like base? Weaker and weaker and weaker.
Yeah. So it's not using induction here. It's using some off-the-shelf PCP theorem.
So it's not actually recursion in some sense.
This stage is not.
This is not. It's not recursion. It's the reason I use this. It's it's like a buzzword, right? It's the way it was conceived maybe 20 years ago.
Iterating. She's not recursing.
There is no recursion here. Yeah.
Iterating once.
She's
sorry. Yeah.
Let me reiterate.
Okay. Did I answer? I mean, there is some other.
It was not recursion.
It's not recursion. That's the answer. Why did you think it was recursion? Okay, so summarizing here, we have this gathering step that increases the jam value, but you lose the 3 coloring structure. And then, right, because these constraints are over larger variables and there's kind of complicated. And then there is this dispersing step which regains the 3 coloring structure. And this is really, one way to view it is that you're replacing each vertex by a bunch of vertices. This is like a gadget. And each edge by some number of edges and maybe some more vertices. Okay, so it's a gadget replacement. Of course, calling it a gadget is not incorrect, but somehow it misses the point that this gadget is really in itself a PCP. Okay? And so because it's a local replacement, you're only multiplying the size of your instance by some constant that depends on the size of this gadget.
I'm not quite understanding this replacement step. So, and the answer to Alex's question. So why is it a different PCP?
Oh, so let me go back to that slide. I just wrote here each vertex splits into several vertices and replace the test by regular edges in a robust way. And the question is, how do you do it? And I said by using a weaker PCP theorem, which kind of implied that you're using whatever it is you're proving. But it's not true. You're using another PCP theorem that someone else proved. Do you see my point? So there is some weaker PCP theorems that are kind of easy to prove. You have a better answer?
I want to state it somewhat differently.
Yeah, okay.
So think of this step as trying to do, you've seen reductions from 100 coloring to 3 coloring.
Right.
Okay. So how do you usually do that? There's some sort of an object called a gadget. And you just stick it in. You say, okay, every time I see a vertex, I'll replace an edge. I'll replace it by the gadget. Now this gadget, where do you find it, etc.? It's sort of hard to conceive, hard to construct. But usually we do it by hand and do something. Here she's finding a very special gadget, which is going to be very good in the relationship between the 100 coloring to the 3 coloring relationship that she's going to get. Where does she find it? It's by a sort of by techniques that were used previously in PCP theorems, but it's not a PCP itself, right? It's just it's a gadget.
It's a PCP with you just don't care about the blow up, or because you apply it to something that of constant size.
Right.
Why isn't it a PCP?
Because it's a gadget. Because the semantics of a PCP wouldn't suffice.
No, it's like you're applying some very special, very sophisticated algorithm on a constant size input. But it's still a sophisticated algorithm.
And you need the assignment testing concept.
Yeah.
It's different from.
Stronger than a PCP, you mean?
It's even stronger than a PCP?
It's much stronger than a PCP.
Okay, so.
Okay, all right.
So it's a stronger PCP on a much smaller object?
It's stronger, it's stronger in one respect and weaker in the respect that you don't care whether, like the blow-up.
So Madhu sort of answered my question, which I was having. Why doesn't the disperse step not just follow from the NP completeness of 3 color?
Right, right.
So why does it not?
Because NP completeness doesn't give you robustness. See,
So you would lose much more in the dispersed step if you did a standard reduction to 3 coloring than you would have gained in the gather step.
You don't want to lose the jam value, you somehow want.
So essentially you have to be, since your thing is sort of size 10,000, okay, this gathering, the neighborhood, or
yeah, whatever.
let's say
100.
250, since that
Yeah.
seems to be the number you like. So
Okay.
assume it's of size 250. I probably have, and you sort of you need 250 to get sort of the jam value to go up by a factor of 2. So,
Yeah.
but since this is so big, you probably have to be able to do your reduction to 3 coloring in such a way that your losing in the jam value is arbitrarily small.
Right, close
I mean,
to
if
1.
you can't do 1 plus epsilon, I mean, if you claim you have a proof which is 1.9, I would sort of have doubts that I really believe you. But so you can actually do one. So the main point is I can do reductions without losing more than 1 plus epsilon.
So
of the jam
if
value.
to be perfectly, how do you say it? The way it really works is that in the first step you gain a factor of 100, and here you only lose a factor of 2. Okay.
So if I'm understanding correctly, the issue is it's a constant size here.
Exactly.
And that's why you can just brute force. You can show it exists and you don't have to worry about it.
For example, except in fact,
She,
and this is
she does
actually
have to worry about the numbers because she's going to keep doing this again and again.
no, but it's some constant number.
But
So
the
it's
factor
actually
of 2,
absolutely
what
right.
you essentially tell me is that for a factor of 2 and an arbitrary finite constraint satisfaction problem, there's reduction to 3 set, which may do a blowout of size in size 500 million,
Right.
but a reduction in the jam value by only 2.
Exactly. Yeah, exactly.
Okay. That's exactly.
Yeah.
I'm also thinking in terms of the slope and the size of the problem.
Okay.
Because if you, let's say, started with the bread and jam, and then you just cloned it, you would double the amount of jam, and you double the amount of bread.
Okay, great.
And
But
then you keep doubling it, and
right. But the
so
doubling
it's got to be less than double.
No, the doubling needs to be as a fraction. So if I cloned it, actually the fraction stayed exactly the same.
Right.
So that doesn't count as doubling.
The definition of jam is the fraction.
Jam is a fraction, so you need to have.
Jam is the fraction.
Yeah.
So the first step really increases even fractionally.
It's how thick the jam is.
It's what kind of jam is.
So it's got to go from 1 out of n to a ratio of 2 out of n.
Or to 200 out of 100n.
Right.
Because n also changed.
Yeah.
But the point is that the thing grew as a fraction. So sham, yeah. Okay.
Why can't you use recursion?
So it's not that. Okay, in the original proof, actually recursion was used, right? They expressed some intermediate constraints as an NP problem and applied recursion on it. So that's why I actually used the word recursion here. But here you don't need it. There is some relatively straightforward PCP construction you can use like off the shelf. So you don't need it. You can try to argue whether it's simple or not. And want to ask any more?
So is the graph getting bigger each time? So I understand this. Now, is the graph getting bigger each time?
Yeah.
But somehow you're able to check it more easily, even though it's getting bigger? Or?
Yeah. So somehow, even though the graph itself is getting bigger, the fraction, the jam value as a fraction of the number of edges in the graph is growing. Okay, so you're only caring about this fraction of edges.
You don't want it to grow too big because there's still a proof. You still have to write out the graph somehow, don't you? In which case,
Yeah, you want your entire procedure by the time you finish, you want it to be polynomial time. So in particular, the end result should be polynomial time.
okay.
But this works out because you just say you multiply the size by some fixed constant every time. You do it logarithmic number of steps.
Okay.
Yeah. Okay. So we said the gathering step increases the gem, and but it loses the structure, and the dispersing step regains the three-coloring structure using this gadget. It's just that I feel insulted by the word gadget, but other than that.
It's good because it's saying that that's all you needed. You just needed to find this one constant size combinatorial object, and then you're done.
Of course, yeah, yeah.
You just don't know how to find it, right?
Is it insulting if you translate it to Hebrew?
It's probably much more insulting. Maybe the contrary, I should say. So this proof is kind of trying to replicate this proof of Omer Reingold of symmetric log spaces in log space. There's this way of, making the graph more and more into an expander. I don't know if you've seen that, but basically you do something which is like a gathering, and then you replace each vertex by a bunch of little vertices. And this second step of replacing is basically replacing each vertex by a constant size expander. Okay? And that's easy to find, right? You just go over all possible constant size graphs, and we know that some of them are going to be expanders, so you just find one. Right? So in an analogous kind of way of thought, you would say, oh, it's the same thing. There is the first step, which increases some value. In Omel's case, it was the expansion, and here it's the jam value. Okay, we kind of understood that. And then there is this dispersing step of making the graph be in the same form that it was before. And in this dispersing step, Omer was able to just plug in an expander that he found by brute force. We want to do the same thing, find this by brute force. Except unlike in the expander world, we have no reason to, there's no way to prove that even if I go over all possible gadgets, there exists a good gadget. So that's why it's not the same.
But the proof goes by
the proof is a PCP. I mean, this is what that proof is. So it's a simple one, but still, it's harder than the proof that a random graph is an expander. Okay. Okay. So then, we've already kind of understood this, that every pair of steps spreads the jam value even further, and still the underlying thing is still a three-coloring. And you can think of it that each vertex is kind of aware of vertices that are in growing distances. And so even though each step is local, the final outcome, every vertex is affected by the entire graph. And if there was a bug, it kind of has been properly spread around. Okay? And so one thing that maybe we will meet later is that I didn't say it explicitly, but for the increasing the jam value step, we really needed to have the graph be an expander. So it needed an expander in the sense that no cut in the graph is very small. Between every two sets of edges, there's a good amount. Sets of vertices, there's a good amount of edges.
Why did you need expander suddenly come in?
Well, how would she have spread it?
So intuitively, you can understand that things won't spread.
I totally understand, but is it now an additional requirement we were hiding up so far?
No, because I'm.
She just wouldn't be able to use it if it didn't
Oh,
get
yes.
spread.
Yes, right. In the first step, you assumed it implicitly.
Yeah, in the first step, there's two answers. Either you can say I assumed that the graph was an expander. That's one answer. And the other answer is you didn't assume that the graph is an expander, but you just added some expander edges, forced them into it. Okay, and then when you said each vertex looks at its neighbors, it's both the neighbors in the three-coloring graph and in this superimposed expander. Okay, so you're forced.
Can you just sort of like do the first step of let's transform it to an expander, three-coloring in an expander graph?
Right, but maybe this is a difficult thing to do, especially if you want to maintain your jam value.
But it happens not to be.
I think it's not good enough to do it at just the first step, but to the graph that she obtains after the dispersing step, it needs to be an expander again.
with the
Right,
same
you may
constants.
have, once you did the other thing, you may have destroyed its expansion.
Even though
does it
I'm
mean
sure
you
you
have to-
haven't, but you
Yeah.
may
But you
have.
have to
Probably not.
prove that.
Yeah, and you don't want to do that.
Also, you don't prove that, so it's
Provided
expander.
with 3 bits, you could do it, I really wouldn't.
No, but so you really prove that the expansion constant stays the same through that
No, you're in much easier situation. Just like with the degree that you asked before, you have much more freedom. You can actually just superimpose an expander on your instance. That's true. So okay, since you're so interested, just say it here. See, in this is where I need it, in this gather step. I said each vertex, in here I'm already ruining the 3 coloring structure anyway. Anyway, my constraints are going to be some crazy thing, right? So it's okay, I'm also going to add, in addition to the edges, I add artificial edges.
Harder. She only makes the, right, you can do it here because you didn't have a 3 coloring problem anyway when you were done.
Right.
But in principle, then it might make that step, that PCP
In principle.
step a little harder.
But since I'm
So
not
she
using...
Gives, she gives every vertex some new neighbors
Which
based
the
on an
artificial
expander
adds.
graph.
Yeah,
Great.
yeah.
Right.
Oh, that's for free. Okay, yes.
Okay, we'll do this.
You should mention that a little over time, but you can keep going for
Are
maybe
we?
like 10
You're
minutes.
kidding.
Yes.
Wow. Okay.
You should wrap up.
Okay. I'm okay. All right. So I have a very nice slide at the end I want to show you. So what is this good for, right? It's not really, the point of this was not for easy refereeing. It's not, the reason that this field has developed so much is because there's a very deep connection to approximation. Approximation lower bounds, right? So just to say it's immediate, right? It's immediate that this robust... Yeah. So the way I should say it is that the fact that the PCP theorem implies hardness of approximation has been like a major drive in the development of this, right? So because they realized this, they were more eager to prove the theorem. Is this right? Probably, yeah.
That really did precede the theorem?
I mean, these all things happens at the same time, but yeah.
Okay.
Definitely before. And this was, so okay, so let me say it like in a dramatic way that I was taught it. This was like a huge surprise, I guess. People worked on hardness of approximation and they had no clue what, why certain approximation problems are hard and so on. And the PCP kind of developed independently. And then when they realized that actually if you prove a PCP theorem, then it would imply hardness of approximation, it was like an amazing connection. Now in retrospect, it's not amazing. It's like syntactic, it's immediate, right? Because, so let's see, remember what we did, we proved that for any graph G, you can robusticize it into a graph H. What does it mean? It means that if you have an approximate answer for the value of H, the robust graph, then it tells you whether or not the original graph has value 1. Right? So of course, if you have a graph G, you want to know whether its value is 1 or not, all you need to do is compute the robust form and then approximate the robust form. Right? But since we know that it's NP hard to compute the value of G, it means that it's hard to approximate. Okay, so now that you understand that this whole PCP is just about doing robustification, it's immediate that it implies hardness of approximation. But at the time, because they were thinking about it in a different language and they had a verifier and a prover and a bunch of things, it was really kind of it's also a very beautiful connection. Anyway, so this was a big drive for many results, and of course, this notion of robustness that we defined for graph G is can be generalized into many other notions of robustness corresponding to different hardness of approximation, notions. So now what should I do? Here is my nice slide. Okay, so let me just finish with this slide, okay? Yeah. I personally don't, as I said in the beginning of the talk, I don't care so much about this story about the refereeing and so on. The reason I think this field is so interesting and and beautiful is because it connects to so many other things, right? So the techniques that you use in proving hardness of approximation are very broad. They go into many different fields. And the reason is because in many different fields you have these robustness phenomenon, right? So, finite fields and low-degree testing, this is like the first kind of robustness phenomenon that were used in PCPs. And then there's discrete Fourier analysis. You have these phenomena in additive combinatorics in many other fields. So it's very nice to see how when you look at one approximation problem, you get into this one notion of robustness. You have another, you have another notion, and so on. And I think it's very interesting to understand what is it that makes these systems, the ones that we have here, robust, and why some systems aren't robust, and kind of to understand these things. But since I'm over time, it will be enough. Yeah. Okay. Okay. Sorry about being over time.
Mean by, say, robustness in this, let me pick this probability phenomenon.
Yeah,
so
I meant to say, but...
what do we mean? So I understand PCPs are robust.
Yeah, so when I said this graph, this three-color thing is, remember we said a graph is robust if whenever there is an almost solution, it can be kind of corrected or traced back into a perfect solution. So think of any system like three coloring, or maybe think of what other example should we take?
Like isoperimetric theorems that if you have a shape that's the ratio of the volume to the area is almost like a sphere, then it should be actually very close to be a sphere.
Right, that's one example. In this approximate groups world, you have, in additive combinatorics where you have a subset of some linear space, and you say if this subset is almost closed under addition, then it must be close to, what are subsets that are closed under addition? Usually it's like subspaces, right? So you say if a subset is almost closed under addition, then it's close to being a subspace. So in general, a robust system will be something where there is some maximal value, and you're saying if I have some solution that has a value that's near maximal, it must be near a maximal solution. There's no way to kind of have this very special behavior that's approaching the maximum without actually being near a maximum. Okay, so it's the opposite of like continuity. If you have, say, a graph that's three-colorable, and you look at a coloring, you make some noise, you get something that satisfies almost all the edges. Here you're saying the opposite. You're saying, look, if I have something that satisfies almost all the edges, the only way to reach it is by a perturbed perfect solution. Okay, so in all of these cartoons, there is such a phenomena hiding underneath there. For example, here, we have these dictator tests, or like these noise stability tests, where you have a Boolean function, and you say, if I put some noise on the function, the most noise stable function is something that depends on one coordinate. And any function that is somewhat noise stable should be somehow close to such a good solution. Anyway.
And in the expanded case, what's the robustness? Because that's the one that you seem to be relying on, right?
I don't know. I have to think about it. It's not something that I can say. Yeah.
So I have a question, which is, so when people think about testing, we distinguish between parameter testing, which is essentially saying that some continuous parameter on a graph, that some parameter on a graph is continuous, and property testing, which sort of says that you can fix something by only changing probability, fraction epsilon of the edges. So could I use the PCP theorem to reduce property testing to parameter testing?
So what's an example of parameter testing?
So it's measuring the density of triangles in a graph.
I see.
So I think also in parameter testing, you have this robustness phenomenon where you say, look, if I have a, you don't.
It's the PCP theorem for an algorithm that is supposed to be sublinear in the input without pre-processing it first. That would be a problem, right? Like the pre-processing you should do to the input graph is somehow inherently going to look at all of its parts. It's like an error correcting code.
But you could view these results as saying that we've identified a subclass of graphs where parameter testing will solve the property testing problem on the original graph. And the correspondence. So that's the robust graphs are those where if you do the parameter testing, that will yield you a property test on the original graph. Sort of.
But the mapping itself is not sublinear, like
right. The mapping is not sublinear.
If you ask me, is there an edge in the robustized graph to answer that question, I probably have to look at many. I have to look at many edges in the original graph.
Right.
But
You're trying to get equivalence.
No, like a linear fraction. It's like an error correcting code. If you ask me what is a coordinate in what is the 10th coordinate in the error corrected version of X, I probably have to look at half of the coordinates of X to answer you that question.
Question on the back.
So, you might not understand the connection to the approximation. Is there a precise connection, say, between the approximation factor you can get in certain problems and whatever this kind of application factor you're getting when you're doing this construction? Because
that's exactly the hardness of approximation factor.
So that factor exactly is.
Because think of this in the three coloring case.
Yeah.
Suppose you were able to take a graph G that's either three colorable or not, and construct a graph H that's either three colorable or no more than 95%, suppose. Then any approximation algorithm that does better than 95% approximation can distinguish between H being perfectly colorable and H being less than 95%. So this is exactly the approximation factor. Christian, actually, I need to hear your question again, but maybe offline. Yeah. Okay.
Right. Thanks again.
Thank you for answering.